Hello, and welcome to the second lecture covering the second section of Chapter 5, a chapter all about light, in particular about how astronomy and astronomers care about light, but also covering the basics. In the previous section, we talked about how light interacts with the world around us and how we understand the world better by understanding how light, interacts with matter, all right? But finally, we're going to discuss what light is, okay? So what is the underlying principle of what makes light, okay? And in doing so, we're going to introduce a concept called the electromagnetic spectrum, which is light, but is a bigger idea than just visible light. Okay, so fundamentally, wasn't the first thing learned about light by any means, but it's a great starting point. And fundamentally, light is a wave and a particle. That's a great starting point. It might be a little overwhelming because it seems like a contradiction, but that's what light is, okay? We call it the wave-particle duality of light. Duality means that something is existing in two states simultaneously. That is light. It also really means that we just don't have the right word in our language to describe exactly what light is, or we don't have the right model. We don't have the right physical analogy to think of light. Because when we think of waves and particles, we're thinking of, maybe microscopic or macroscopic, but things that we can really directly measure. We can't directly measure light. We can't take one particle of light and put it on a scale, okay? It interacts directly with the scale. It is part of the fabric of the universe in a sense, okay? But we still have some good estimates about how it conserves energy and momentum and ideas like that, okay? And that's really where the concepts of particles of light come from, this understanding the pieces of the universe at their smallest indivisible level. And one of those indivisible parts of the universe is a photon. In the same way that an electron is an indivisible piece, a tiny piece of matter, a photon is a tiny piece of light energy. It does not carry mass. Photons do have no mass at all. They're massless, but they do carry energy, and they are the particles of light. So when we talk about red light, we are talking about the wave of red light, okay? And maybe you think of just a ray of red light, but that ray of red light is certainly a wave, but it's also a particle, okay? Now, what we will see is some trends, because it's not just completely ambiguous and we can't really determine if it's a wave or a particle. We don't know anything. Don't lose hope about light. There are certain conditions where it's best to think of light as a wave, and other conditions where it's best to think of light as a particle. And in a pretty clear-cut way, if light is traveling through something, if it's just traveling through space, open space, then it's going to behave as a wave. So the propagation of light is well understood as a wave. When light interacts with matter, in particular, when it interacts with other small particles like electrons, it really behaves irrefutably behaves like a particle, smashing into those electrons and bumping them out of the way in a way that a wave simply can't do, at least a mechanical wave, our understanding of waves. Okay, so interesting properties of light. And let's elaborate on some more, because we should make sure we're clear on what a wave is. Well, a wave, it does include things like sound waves or ripples in a pond. Okay, it's the same fundamental principle. So when we do talk about light being a wave, it includes all of these properties. Okay, so it is a pattern of motion that can carry energy. All right, it doesn't carry the surroundings with it. So, for example, the ripples in this pond don't carry the water with them. They just are this manifestation of energy passing through the pond, all right? Now, the energy dissipates, which is why the ripples get smaller with distance, but light can travel through the vacuum of space. It doesn't need a medium like water in the case of these ripples, because the ripples can't travel without water, right? The ripples don't travel through a vacuum. Light does, and light is unique in that way, because even sound is a wave, but sound cannot travel through a vacuum. Every space show or movie that shows spaceships exploding and then other spacefaring people hearing that explosion in another spaceship isn't possible, because the sound would not be able to travel through the vacuum of space. But light does, and it's the only wave that does. Okay? Now, a property of waves, an important quantity, is the wavelength, and it's the distance from one peak to another. Okay, so one high ripple to another in this case. So here it is shown from a side view. All right, this is a side view of a wave. Okay, in math, this is called a sine curve. all right? But it's a perfect wave. And one peak to another is a wavelength. The letter that is used for the wavelength is a Greek letter, all right? And it's lambda, and it's drawn like this. So when we use that variable, we mean wavelength. Now, waves don't just have wavelength because that's just a distance, because after all, waves are going up and down, so they also must have a quantity known as frequency, the number of times a wave goes up and down per second. So in other words, if someone was to stay at a fixed point and just measure how much time it took the wave directly in front of them to go from a low point up to a high point and then back down again, because that would be a complete cycle. Well, if they measured how long that took, or more accurately measured how many times it did that per second, they would have the frequency, because the frequency is vibrations per second. Okay, and if something's going very quickly, obviously it can vibrate many times per second, and light tends to be very, very fast in vibrations. Okay, unimaginably fast in some sense. Okay, very, very quick. Okay, but that all waves are expressed in terms, or completely, right? They can be defined by their wavelength and their frequency. Okay, now they also carry an amplitude. We are not going to talk about it here with light. It's not terribly relevant. But if we were completely describing a wave, the amplitude of the wave, kind of the height of the wave, also would carry information about the wave. Okay, but here we just care about the wavelength and the frequency. Now, if we know these two things, by the way, two quantities, right, the length of the wave and how many times per second it goes up and down, then we can calculate its speed directly by just multiplying them together. Wavelength times frequency is speed, how fast the wave is traveling. So from the perspective of our stick figure, it would just be how fast the wave flies past them, right? So one point on the wave, how fast is it flying by if they're just standing there at rest, okay? Now, mechanical waves, whether they're the ripples in the pond we saw, or sound waves, or earthquake waves traveling to the ground, all of those types of mechanical waves, they all travel at different speeds depending on the properties of the medium that they're traveling through, okay? Sometimes also depending on the properties of the wave, but usually on the properties of the medium. Light is an exception. Light is a fundamental aspect of the universe, and it sets the rules of the universe in a sense, the same way that gravity does and these other fundamental rules. And its speed is absolute. Its speed is always 300,000 kilometers per second. All right, so light always has one speed. Right? Light will never travel at a different speed in the vacuum of space. It never speeds up or slows down. The vast distances that light travels, and the time that it takes to travel, millions of years, for example, billions of years. When we look at objects that are billions of light years away, we look at light that has been traveling through for that amount of time, uninterrupted through space. And in that process, it is never slowing down, just maintaining that same speed. And if that wasn't a big enough idea, I'll touch on another one briefly, but not to get off topic, that this speed not only defines all light, so it says that all that light must travel at speed, the speed is also completely separate from how fast you are going as an observer. So this person, like our stick figure, they could be going in the same direction as the wave at a speed of, say, 290,000 kilometers per second. So just a little bit slower than light, which would be quite a feat, but that's a story for another day. And they would still see the light traveling at 300,000 kilometers per second, even though it should be the difference if light behaved like any other wave or anything else, but it isn't, because again, light is part of the fundamental fabric of the universe, which I mentioned in the last video. Okay, now light is a little bit more abstract than a ripple in the pond. It's what's known as an electromagnetic wave. In a simplified way, we could think about it as a curve here that has a bunch of electrons, okay, charged particles, part of atoms, sort of representing the surface, sort of almost representing a string, right? So it's like a wave traveling down a string, like a guitar string, but our string is composed of electrons all strung together, okay? And so when the light passes, okay, by, they pick up that signal. They move with the vibration, okay? So honestly, here, it's best to think of the electrons as the medium, okay? There's an electric field that's part of the wave, okay? But here, this is the medium, and it's being sort of interacted with by light. A light wave traveling through. Light doesn't need a medium, but it can have one, and it will have an effect. It's a vibration of electric and magnetic fields. Okay, light is composed of those two types of fields. It has a magnetic and electric component that self-propagate each other. It is actually, that is why it can continue and it doesn't need more energy. It doesn't run out of energy. The light never dissipates any energy, okay, until it gets absorbed by something, but then that energy ultimately will be conserved and re-emitted. Of course, you can produce light by, say, converting matter into pure energy, but once it's traveling through a vacuum, doesn't just, there's no friction. It doesn't experience anything like that. Now, light interacts with charged particles, okay, quite readily. It's a big part. You can't understand charged particles, in fact, without understanding light. In the realm of modern physics and particle physics, the photon, the particle of light, is the carrier of information for electricity and magnetism itself. It's the fundamental idea about how electromagnetism works. All right, but back to some details about waves. Now, when we talk about a wave, for example, a wave that has a length of 1 centimeter, well, if that wave is light, then the frequency is 30 gigahertz. Seems like a really big number, but the reason is because we have that the speed of light, c, is equal to frequency times wavelength. Now, c is 3 times 10 to the 8 meters per second. Now, you might be saying, wait, wasn't it 300,000? Well, that was kilometers per second. Here, if I want to be able to work something closer to centimeters, I'm going to stick with the base units of meters. And then I know my frequency is what I'm interested in, but I know the wavelength, I'm told it's 1 centimeter, which is just 1/100th of a meter. So then if I solve for f, well, f then is going to be the 3 times 10 to the 8 meters per second divided by that centimeter, which is just 1 times 10 to the negative 2 meters. Well, if I have this and I'm taking a 10 to the 8 and I'm dividing by another 10 to the negative 2, I'm going to get a 10 to the 10. So then I have 3 times 10 to the 10, and my meters canceled, so I'm just left with 1 over seconds, precisely the units of hertz. So good there. All right. Well, 3 times 10 to the 10 is 30 billion, and 30 billion is 30 giga. A giga represents a billion, so uppercase G is just proportional to 10 to the 9. So you can see that's exactly what we have here, because if we move the decimal place over 1, we get 30 times 10 to the 9 hertz, because that's 1 over seconds. So that's the same as 30 gigahertz. And I won't do that again with all the other examples, but there you see exactly what the speed of light means, why it gives us some really, really high frequencies, okay, for light, okay? So interesting thing about light, it vibrates at incredibly high frequencies, incredibly high, right? We're talking 30 billion times per second. This wave is going up and down. The electromagnetic phenomenon that's creating it and propagating it is going back and forth that many times per second. And I make a big deal about it because if we compare that to the wavelength, well, the wavelength is entirely macroscopic, 1 centimeter, right? What type of light has a wavelength of 1 centimeter? Well, not the type we can see, all right? If visible light was that long, I mean, we would notice it in a very different way. Our eyes cannot see wavelengths that long, and in fact, wavelengths this long don't carry as much energy as shorter wavelengths, like the type we can see, or even shorter wavelengths that are harmful light. A wavelength like this is precisely a microwave, like the kind that we use to cook food, although not necessarily the exact same length. But you might then pause and say, wait, microwaves actually do heat things up really well. This is just because of the unique property of the wavelength, not so much that they are high energy waves in general. There's just special spots, special values, all right, that have sort of sweet spot properties in terms of the vibrations. This concept, by the way, continues. again, without as in-depth calculations, but if you see here, if we shorten the wavelength, so make it half as long as it was before, so we have a smaller wavelength here, it is now, we can call this one wavelength 2. It's 1/2 of wavelength 1, right? Just to reiterate the use of the lambda for wavelength. Well, that means that the frequency has to go up by 2, because the speed of light, c, cannot change. It's a fixed value, all right? Hopefully I've got the idea across. So cutting the wavelength in half gives us twice the frequency. If we cut it in 1/4 of what it started as, then we get 4 times the frequency. So we see what happens. Light, the frequency and wavelength for light is absolutely tied in together. You can't change one without changing the other, okay? A constant value. So if you know wavelength, you automatically know frequency. Particles of light are called photons. I mentioned that a few times. Each photon has a wavelength and a frequency. Weird for a particle, right? Okay, but they're tied together. The frequency tells us more about the particle itself, because the particle can be thought of as representing the conservation of energy per particle, and the frequency is directly tied in with the amount of energy per particle, okay? Now, so is the wavelength, all right? But the frequency is usually what we think of when we think about the energy of the photon, okay? It depends on its frequency. All right, so here are some formulas. Let's zoom in and take a look. So this is lambda times f equals c, or wavelength times frequency, wavelength times frequency equals the speed of light. All right? Lambda is wavelength, f is frequency. C is the speed of light, a constant, fundamental constant, never changes, right? It's not 3 times 10 to the 8 meters per second sometimes, and sometimes a different value. It's always 3.00 times 10 to the 8 meters per second, okay? All right, and this is in the meters version because meters are the fundamental unit, even though you often see it in kilometers. We would read this as 300 million meters per second. All right, here's a new one we haven't seen. The energy per photon is h times f. See, that's the relationship, see? So we got the wave properties and the particle properties working together, unique to light. We couldn't do this for any other phenomenon, okay? What is h, though? Well, it turns out h is another fundamental constant, right? One of the very important ones. It is 6.626 times 10 to the negative 34 joule seconds, okay? That'd be JS if you were writing out the units. Okay, it's known as Planck's constant, named after the physicist who started using it to understand initially heat being emitted from objects, okay, and which of course they ended up tying in with light in the way that light is quantized, which means it's broken into little indivisible particles, indivisible photons. Let's do a thought question. The second from the chapter, first in this video. Which of the following light waves has the most energy? The top, the middle, or the bottom? All right, think about this carefully. All right, pause the video if you need to, and make sure that you can answer this question. Okay, let's see. It's the bottom, all right, because it has the smallest wavelength. Okay, if you compare between light, the light with the smallest wavelength will always be the one that carries the most energy per photon, okay, invariably. Now, let's do a little side topic here. Turns out that light is polarized. What that means is that light, being a wave with crests and, high points and low points, top of the wave, crest of the wave, trough of the wave, that with those properties, they can be tilted in lots of different ways. It's a 3-dimensional wave, and that allows it to be polarized, okay? Technically, any transverse wave can be polarized, so can ocean waves. By the way, sound waves are longitudinal waves, so they cannot be polarized. But what is it? What the heck is polarization? Well, it describes the direction, as I was saying, that the light wave is vibrating, all right? Because it's going up and down, but exactly what direction is it going up and down? Now, reflection always changes the aspect of polarization, and so can transmission through something like sunglasses, okay? Now, bigger idea, the electromagnetic spectrum, all right? This figure is a fundamental summary of light, okay? There's a lot to unpack here, but let's just go through each row rather quickly, but each row one at a time. Okay, so the top row here shows the entire electromagnetic spectrum from the shortest wavelength to the longest wavelength. I start by mentioning wavelength because first of all, it's shown here in the second row, so it'll be the next one we talk about. And I think the figure shows that most directly because we can clearly see that on the left-hand side, the waves are tighter together. And then as we move further to the right, they get much more spread out. So we can see the visualization, all right? Not to scale, by the way, but still, demonstrating the change all the way from the shortest wavelength light to the highest wavelength light, okay? Visible light is kind of right in the middle, okay? And it just is the light that is the peak wavelength of our local star, the sun, okay? Furthermore, it's the light that our atmosphere, which has been around for billions of years, is most transparent to, based on the composition of the atmosphere. So humans evolved to take advantage of that light. All right, so that's why we see the rainbow. There's nothing special about the rainbow. It's just the light that was available to the organs of our eyes. Okay, so what else do we see in the figure, right? Well, we see that there's light to the left and the right of visible light, so light with shorter wavelength and light with longer wavelength, okay, going in the shorter direction, all right, and the long direction. All right, so when we go in either of those directions, we see, all right, the wavelength either getting shorter or longer. That means that ultraviolet light is short wavelength light. X-rays are even shorter. Gamma rays are the shortest of all. On the other side, infrared is longer wavelength light, and microwaves are longer still, and past microwaves are plain old radio waves, which get really long and are the longest. All right? In meters, if we want to put some numbers on here, we can see that gamma rays are about 10 to the negative 12, so incredibly short, smaller than an atom, all right? Then we get up to X-rays on the smaller side, become the size of a hydrogen atom at 10 to the negative 10. 10 to the negative 10 is this kind of a special value, often called an angstrom. It's not kind of one of the official prefixes for small values like nano and pico and so on, but since it's the size, kind of an average size of a hydrogen atom, it's a good comparison. Then right at the kind of the upper end of X-rays, so the longest X-rays, or the shortest or the very shortest of the ultraviolet, we get to a length around 10 to the negative 8, getting to the smallest complex biological molecules like proteins, okay? Once we get into visible light, we get to something like a bacteria, which is relevant because if you think of a visible light microscope, that's about the smallest thing that scientists can see with such a microscope. When scientists go smaller, they actually don't use light at all. They use, well, electrons, which is a whole nother story, but essentially electrons are also a wave and a particle. Electrons also have a wave-particle duality. But again, off topic. Point being is that things like proteins you cannot see with visible light. You just simply can't because they're too small. They're smaller than the wave itself, okay? You can't see an atom with visible light because the atom is much smaller than light, much, much smaller, okay? In fact, you can see that the size of visible light is 10 to the negative 6, just a little bit less than 10 to the negative 6, right? Because if 10 to the negative 6 would be a millionth of a meter, called a micrometer, mu-m, and we can see that visible light falls just a little bit less. Interestingly, because it falls just underneath what a common prefix for a small value, people always refer to the range of visible light, I guess a little bit tighter than that, so right about there, always refer to that range, which is 10 to the negative 7, but we call it hundreds of nanometers. So it's 10 to the negative 7, but you'll always see it expressed, or most commonly, in hundreds of nanometers, okay? Where a nanometer is 10 to the negative 9. So in other words, 100 times 10 to the negative 9 is the same as 10 to the negative 7 if you just consider moving the decimal, okay? Well, anyway, as we go to longer waves, we get to, infrared waves, which become, much, so long that they're the size of a whole cell, right? So you definitely couldn't use a infrared microscope to do much of anything useful, right? Because couldn't even see a cell, right? And we keep going, we get up to microwaves. Microwaves are a few centimeters long, right? The longer ones, I think the ones that are good for cooking food are around 2 centimeters, but they go up into the tens of centimeters. And then once we get past that shorter end of radio waves, because microwaves are just the shortest of the radio waves, their name can be confusing because when you hear micro, you might think, oh, those must be the shortest of all the waves. No, they're just the shortest of the radio waves, but radio waves are all long waves. And then the radio waves become many, 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 many meters long, even kilometers long in some cases. But radio waves, they are very low energy, because the other side of the story is that since wavelength goes up in one direction, that means that frequency must go up in the other direction. So that means that the lowest frequencies are going to be for the longest waves, all right? So, and I guess over here I put the wavelength, I said up, and I drew it in this direction. Sorry if that was very confusing, right? The wavelength goes up in this direction, right? And then the frequency goes up in the opposite direction. My goodness, there we go. I don't want to close out the slide because I'll lose the other writing. But you can now see with some little blocks, we go up, right, in this direction. So longer and longer wavelengths as we move to the right. But that dictates, right, that the frequency must get longer and longer as we move to the left, right? Because we're talking about the same light in both cases, right? Because as we know, since the speed of light is fixed, wavelength goes up, frequency must go down, and vice versa. All right, so the very long waves, like those football length field radio waves, well, they have relatively low frequencies. Now, low for light is a million times per second, so 10 to the 6 times per second, but that is in fact very low for light, especially compared to gamma rays or X-rays that are oscillating at rates, so vibrating at rates of 10 to the 18 or 10 to the 20, right? 10 to the 18, by the way, would be it's a million trillion, all right? So that's important because if you recall, the energy that light carries per photon, which is also often the energy that light carries if you keep all the photons comparable between your light sources, well, it's tied in directly with the frequency. So that means that gamma rays carry a lot of energy per photon, 10 to the 6, as compared to radio waves that carry 10 to the negative 8 energy per photon. Now the units here are units what are called electron volts. Now, electron volt is a unit of energy which is equal to 1.6 times 10 to the negative 19 joules. So electron volt is precisely 1.60 times 10 to the negative 19 joules. So it's a unit that's used for small quantities of energy that's tied in with other fundamental electromagnetic quantities like the volt, okay? And so that's the electron volt, a measurement of energy for photons, okay? Because photons carry energy. Again, they don't have mass, but they definitely carry energy. So one photon of a gamma ray would carry 10 to the 6 electron volts, so a million electron volts. If you note, if you think about the actual amount, you multiply 10 to the 6 by 10 to the negative 19, so you'd still have 10 to the negative 13 joules, which is still a tiny amount of energy, right? So, come on, big deal, right? But that's just one photon. So a small amount of light, like a tiny, LED that is, barely glowing, right? And using a tiny, tiny voltage or something, so very, very little energy. Even that is emitting millions, trillions, honestly, of photons. So, a photon is such a small amount. So to carry this much energy per photon is a big deal. So much so that gamma rays are considered incredibly harmful. Gamma rays are produced in very high energy nuclear reactions. Gamma rays exist in parts of space where things like neutron stars are crashing into black holes and so on. They can carry so much energy that photons, that just a few photons could tear apart a human body. So because, and by few, I guess I mean, millions, but that's all it would take, right? Considering that usually there's trillions upon trillions of photons. But again, on the other end, I think we should notice the scale of energy here, because compared to radio waves, the number of tens, right, the multiplication factor in tens is a difference of 14, because we have 6 and negative 8. So we have a difference of 10 to the 14, which is to say that gamma rays carry 10 trillion, all right, because this is 10 or 100 trillion. So 100 times 10 to the 12, right, 10 to the 12 being a trillion. So again, gamma rays carry 100 trillion times more energy than radio waves. All right, so there's really high energy light out there, like gamma rays, and then on the other end, dramatically less energy carried in radio waves, those long waves. Okay, all right. And I keep mentioning gamma rays because they're on the extreme. You probably know more about X-rays, right? Because X-rays are actually applied, but even when they're applied in medicine and helpful, we always acknowledge their risk, right? You want to limit your exposure to them just because they do carry so much energy that they have a propensity for killing cells, right? They carry enough energy or are making DNA reproduction go haywire, right? Just because they can interact with organelles of cells, things at the microscopic level. So in the last couple things here, which I won't spend as much time on, there is a row here for sources and a row for cosmic sources. So kind of ground-based, terrestrial, and then cosmic. So you can see, radioactive elements and X-rays and, for the harmful stuff on Earth, because those short wavelengths are harmful. Light bulbs right in the visible, right? People, you notice, are infrared. That's referring to the fact that we are an emission source, but an emission source that for us is invisible light. We can't see infrared. Right? But if we have infrared goggles that are, they're detecting infrared and then translating it to some scale that we can see, translating it to visible light, then we'd see the heat signature, right? Well, that's infrared, all right? And right on to radar, microwave, and then more radio. As far as sources in space, gamma ray bursts are these incredibly dramatic phenomenon that happen in distant galaxies. Black ray or black hole accretion disks are a known source of X-rays. That's due to basically very, very hot, so superheated gases to tens of millions of Kelvin, which would be temperatures only on the interior of stars normally, but these are surface temperatures, so they're emitting light at such a high thermal frequency corresponding to that high temperature. But most stars are going to be emitting light in basically the visible spectrum, many of them, but some have peak wavelengths in the ultraviolet. Okay, we actually have a part of the sun that emits ultraviolet. It's chromosphere, but that's obviously invisible to the human eye. We don't see that signature. And furthermore, ultraviolet, besides the very shortest of the ultraviolet, so the ultraviolet is closest to the visible spectrum, most ultraviolet is absorbed in our atmosphere, so it never makes it to our eyes to begin with if we're living on the surface of Earth. But there are some, and there are some hotter stars that actually emit much more ultraviolet than our sun in the population of stars that we know of, that we surveyed in our galaxy and others. Going on to sources of infrared, planets glow in the infrared. So often science that involves studying planets is very interested in infrared, and so are distant galaxies. Okay, so somewhere between star-forming clouds in the infrared and the cosmic microwave background, which is the most distant signature there is, there's a whole slew of other infrared research in the most primordial galaxies. Not because they're actually infrared, but they've been shifted there with something called the Doppler shift, a topic that we'll discuss at the very end of this chapter. And then there's also, interestingly, on the very, very far end, so the longest wavelength, least energy light, there's things called radio galaxies, which might make you think, oh, well, we were just talking about these primordial galaxies and the shift. Is this an even more extreme case? Well, no, actually, radio galaxies are very high energy galaxies with what is understood to be a very active supermassive black hole at the center, which is creating huge jets of incredibly fast electrons that, most importantly, are accelerated very quickly, and in their acceleration create a essentially radio antenna, and that radio signal is what we see, and then we can look at other parts of the spectrum to investigate. But yeah, so they're plumes from black holes, not because black holes emit anything. If you've ever heard of black holes, they eat everything, but they also there's a lot of activity right at the edge of the black hole before things fall in, and that creates these huge bursts of energy. So many different sources, a lot of different stories to tell. Obviously, the electromagnetic spectrum is just the backbone of understanding in astronomy, because everything that astronomers do involves looking at the different parts of the spectrum and observing, either in radio, gamma, and everything in between. True or false question for you. The highest energy photons have the longest wavelength. All right, make sure you can answer this one. So it's good to be able to confidently answer a question like this. You got it? False. No way. The highest energy photons have the shortest wavelength. Okay? They also have the highest frequency. All right? So the higher the photon energy, the longer, so it should be the, not he, the shorter, or is energy independent of wavelength? The shorter, right? Because it's definitely not independent, right? But by the way, you haven't seen it in one equation, so I could see why you might think that. But if you recall, the energy per photon is that constant known as Planck's constant times the frequency. But recall also that the speed of light is wavelength times frequency. So you can then solve for frequency from the second formula, and it's just the speed of light divided by the wavelength. And then if you, whoops, that should be an F. Right, so I solved for this one. Right, it was divided both sides by lambda. So the frequency is the speed of light divided by the wavelength, c over lambda. Well, now I'm going to substitute that in to the energy formula, and we can then have a direct formula that shows that we have Planck's constant, just a known constant, all right, times another known constant, the speed of light, over the wavelength. All right, so yeah, there's a direct relationship, right? As lambda goes up, E goes down. Nice. So what have we learned in this section? Okay, we learned about particles of light, that's what light is. It's a wave-particle duality, all right? We've learned that light vibrates. It has a quantifiable frequency, which it tells a lot about its energy, all right? We've learned a lot about the particle of light and the importance of thinking of it that way. And, big idea, we've learned about the electromagnetic spectrum. We'll come back to that idea, certainly, okay? Where how we've learned how the human eye can see a small part of it, right? We saw it was a tiny little wedge, okay? And an entire range, okay, includes a lot of things that you don't necessarily think of the light, but they're all photons. They're all just composed of different wavelength, different frequency photons. Okay, well, that is it for this section. Stay tuned for the next section as we continue to talk about light and its importance in astronomy.